Welcome, students, to the captivating realm of physics, where curiosity meets discovery. As we embark on this intellectual journey, I encourage you to explore the wonders of the universe, from the smallest particles to the vast cosmos. I invite you to view our latest video, which delves deeper into this fascinating subject. Kindly subscribe to our channel for ongoing insights and discussions that will ignite your passion for learning. Together, let us uncover the mysteries of nature.
Dear students, in this video we are going to study about the phenomenon of interference, constructive and destructive interference expressions for amplitude and intensity.
The intersection of two independent light waves traveling through space creates a distinct, highly energetic ripple pattern known mathematically as interference. We see this clearly in the physical world when a stone is dropped into still water. As the wavefront spread, the molecules oscillate, and the light reflects off the overlapping peaks where these ripples meet. Model this with two sources, S1 and S2, emitting waves meeting at intersection point P. Under the principle of superposition, their displacements add algebraically into a single resultant wave. The light's intensity is entirely determined by the phase difference between these waves. Adding two light sources is a strict geometrical calculation. The timing of the waves and the distance they travel dictate whether the intersection becomes brighter or fades into darkness. To calculate this, we define the first wave arriving at point P as y1 equals a1 times the sine of omega t. Here, y represents the instantaneous displacement, a is the maximum height or amplitude, and omega defines the angular frequency. The second light wave arrives at the same frequency, but from a different origin, expressed as y2 equals a2 times the sine of omega t plus phi. This variable, phi, is the phase shift. It represents the spatial or temporal lag between the two waves. Applying the principle of superposition, the resultant wave is simply the sum of y1 and y2. Through trigonometric expansion, these two independent formulas resolve into a single, unified resultant wave, y equals capital A times the sine of omega t plus theta. No matter how many waves intersect, the physical result can always be predicted by resolving them into one resultant mathematical wave. To find the height of this new wave, we use the amplitude equation. Resultant amplitude equals the square root of a1 squared plus a2 squared plus 2a1a2 times the cosine of phi. Since the original amplitudes are fixed, the final size of the wave depends entirely on the cosine of phi. If the phase difference is an even multiple of pi, the waves are perfectly in phase. In this state, the cosine term evaluates to exactly 1. The peaks reinforce each other to create constructive interference, resulting in the maximum possible amplitude, a1 plus a2. When the phase difference is an odd multiple of pi, the waves are completely out of phase, and the cosine term evaluates to -1. Here, a crest meets a trough and they cancel out. This is destructive interference, forcing the minimum possible amplitude. This means light plus light can result in absolute darkness. It is the mathematical limit of two waves working against one another. While our equations track amplitude, the human eye perceives the physical energy of the wave, which we measure as intensity. Intensity of light is directly proportional to its amplitude squared. Squaring the amplitude equation reveals the full intensity formula, I1 plus I2 plus 2 times the square root of I1 I2 times the cosine of phi. This final interference term modulates the baseline brightness. This term only exists because light behaves as a wave. It creates a landscape of fluctuating energy that particles simply cannot replicate. Where the constructive equation reaches I max, light concentrates into a bright white band. Where the destructive equation reaches its minimum, light collapses into a dark gap. Across a physical screen, these alternating bright and dark strips appear. These are interference fringes. It is important to note that the darkness of a fringe does not mean the light's energy was destroyed. Instead, the wave nature of light redistributes that energy, siphoning it from the dark gaps and piling it into the bright bands. The resulting pattern of light and dark bands is the highly predictable physical manifestation of algebraic wave addition.
Now let us study about the phenomenon of interference. What is interference of light? That's the phenomenon of superposition of two light waves, which produces increase in intensity at some points and decrease in intensity at some other point, and that is called as interference of light. This superposition of waves refers to addition of waves. The concept of superposition of mechanical waves that was already studied in 11th standard. When two waves simultaneously pass through a particle in a medium, the resultant displacement of that particle is the vector addition of the displacements due to the individual waves. The resultant displacement will be maximum or minimum depending upon the phase difference between the two superimposing waves. These concepts hold good for light as well. For this explanation, let us consider two light waves from the two sources S1 and S2 meeting at a point P as shown in this diagram. The wave from S1 at any instant t at P is given by y1 equal to a1 sin omega t, and the wave from S2 at an instant t at P is given by y2 equal to a2 sin omega t plus phi. The two waves have different amplitudes a1 and a2, same angular frequency omega, and a phase difference of phi between them. The resultant displacement will be given by this expression y equal to y1 plus y2, that's equal to a1 sin omega t plus a1 sin omega t plus phi. Simplification of the above equation by using trigonometric identities will give y equal to a sin omega t plus phi plus theta here in this case, where this amplitude a is given by root of a1 square plus a2 square plus 2a1 a2 cos phi, and here theta is given by tan inverse of a2 sin phi by a1 plus a2 cos phi. The resultant amplitude is maximum, and the expression for that maximum amplitude is given by a maximum equal to root of a1 plus a2 the whole square, and this is when phi is equal to 0 plus or minus 2 pi plus or minus 4 pi etc. The resultant amplitude will be minimum, and thus given by the expression a minimum equal to root of a1 minus a2 the whole square, and this arises when phi is equal to plus or minus pi, plus or minus 3 pi plus or minus 5 pi. Here all the things are odd numbers. So here in this case even numbers will be there, and here will be odd numbers. The intensity of light is proportional to the square of the amplitude, and that's given by I proportional to a square. And squaring the equation on both sides, that is equation 7.10, we have I equal to I1 plus I2 plus 2 into root of I1 I2 cos phi. And in this equation 7.15, if the phase difference phi is equal to 0 plus or minus 2 pi plus or minus 4 pi, it corresponds to the condition for maximum intensity of light, and that is called as constructive interference. So this is the case for constructive interference. Now, the maximum intensity will be given by this expression, that is the resultant maximum intensity. I max is proportional to a1 plus a2 the whole square, and that's equal to I1 plus I2 plus 2 into root of I1 I2. Now let us see about the destructive interference. So in this equation 7.15, if the phase difference phi is given by plus or minus pi, plus or minus 3 pi, plus or minus 5 pi, that is odd numbers, odd integers, it corresponds to the condition for minimum intensity of light, and that is called destructive interference. The resultant minimum intensity is given by the expression I minimum proportional to I1 minus A2 the whole square, and that's equal to I1 plus I2 minus 2 times root I1 I2. And as a special case, if A1 will be equal to A2 and that's equal to A, then the equation 7.10 that will become, so this equation can be written as A equal to root of 2A square plus 2A square cos phi, and that's equal to 2A square cos square phi by 2. And therefore A can be written as 2A cos phi by 2. That means the intensity I is greater proportional to 4A square cos square phi by 2, since I is proportional to A square. So the intensity I can be written as 4 times I naught cos square phi by 2, as I naught is equal to A, is proportional to A square. And the maximum intensity is given by 4 times I naught, when phi is equal to 0, plus or minus 2 pi and 4 pi, etc. And I minimum equal to 0 when this phi has the value of plus or minus pi, plus or minus 3 pi, plus or minus 5 pi, etc. So we conclude that the phase difference phi between the two waves decides the intensity of light at that point where the two waves meet.